motion, no? So roughly speaking, what is your Brownian motion? It starts with 0, means B of 0 is equal to 0. Okay, it has independent increments and stationary increments, and not only that, that bt minus b of s, this is normally distributed with mean 0, variance t minus n. So that means it is basically the process whose path is continuous almost surely. Okay, and not only that, this is not only continuous, but you can expect more regularity that we have seen, that is using so-called the Kolmogov's continuity theorem. So Kolmogov's continuity theorem is basically a general statement. That means if you have a say stochastic process xt, okay, which has a continuous sample path, then, and if you have this property that expectation of xt minus xs to the power beta for some beta, if it is less than equal to some constant times t minus s to the power 1 plus alpha, okay, if this holds for some constant beta alpha which is positive, c is greater than or equal to 0, then what it says that, then if you look at the exponent gamma, which is less than alpha by beta, then if you look at the path t goes to x of t omega, then it is Hölder continuous with exponent gamma. Okay, so in particular what it says that probability almost surely x of t omega minus x of s omega, this is less than equal to k times mod of t minus s to the power gamma. This holds for all t and s belongs to 0 to any given capital T, and this constant k depending on basically your capital T also, omega, and the exponent gamma. Okay, so this is Kolmogov's continuity theorem, and we try to apply this thing for the Brownian motion, and then we have seen that the path of a Brownian path is Hölder continuous with the exponent gamma, which is strictly less than half. Okay, because we already seen that if you look at bt minus b of s, then to the power say 2 of m, we consider beta is equal to 2 of m. If you look at that expectation, okay, then you are saying that this is some kind of t minus s to the power m, because bt minus bs, this is normally distributed mean t and variance s, and then you know, because from there we know the what is your density functions and so on, so that I can find the expectations, okay, for some constant c, and hence actually what I can have that beta, if you consider, so this actually you can write down no 2 of m, which is your beta, and this is your m plus 1 minus 1, you can put it from there. You see that this gamma, which is actually less than half. So the path of the Brownian motion is of Hölder continuous, uniformly Hölder continuous of exponent gamma, which is less than half. And not only that, as a consequence, what we have proved, not a consequence, we proved as a theorem that if you consider the exponent gamma, which lies between open half to close one, then there exists no s. It is nowhere Hölder continuous with the exponent that part. Okay, so using this theorem as a consequence, we have proved that the Brownian path are nowhere differentiable, because if it is differentiable, then it is Hölder continuous exponent gamma is equal to half, and your previous theorem says that this is not the case. Okay, so it is nowhere differentiable. And another thing is we have proved it that if you consider any say finite interval, okay, it is of infinite variation. It is of infinite variation. Again, because of this theorem, so basically why? If sample path is of say finite variation on some sub-interval, then we know that it will be differentiable almost everywhere there. Okay, so that is in your analysis course we have done it. But the theorem says that this is nowhere differentiable. So it is of infinite variation. But okay, these things actually one can do it using quadratic variations, and then the path continuity of Brownian component also one can check there that it is of infinite variations. But using these things also one can conclude that it is of infinite variations. So why these two striking property I am discussing again? Actually, okay, this is out of our syllabus in this course. So actually we want to define 0 to t something some f of say s d of b of s. Okay. So the stochastic integral with respect to the Brownian motion. So how to deal with that? Because okay, if I think of for each omega, then it is a kind of real case. So to define that things, what we know that okay, if it is of infinite variation, it is a finite variation, then I can define it. That is called the Riemann-Stieltjes integral. Or if is b is differentiable, I can think of this is nothing but my b prime of s is of ds f of s integral over 0 to t. These things, is it not? So that I can do the Riemann integral in a classical sense. But in this case, we can't do these things because the two striking property which should hold for Riemann-Stieltjes integral, it is not satisfied here. So that is why the concept called the Ito calculus comes into picture, and so it is completely new calculus one is to think of. Okay, that is the Ito calculus. That is called the Ito calculus. So the classical integral or the classical Riemann-Stieltjes integral concept does not hold here. So because of these two striking property of a Brownian component. Okay. On the other hand, what we have proved, see B of S, it is again a martingale that we have seen it. It is a martingale. Using our general example, I have proved it. No, so if you look at the filtration, which is the natural filtrations, okay, generated by the Brownian motion itself, and then it has a independent and stationary increments with expectation of Bs is equal to 0. Because Bt minus B of S normally should mean 0 variance T minus S. And B of 0 is equal to 0 almost surely. So from there I have seen that expectation of B of T is equal to 0 for all T, and hence Bt is a martingale. Okay. And not only that, we can expect, see, since B is a martingale, that B square T is a semi-martingale. Is it not? Now you know that Dup's decomposition. So if you have a semi-martingale, then you can decompose as a sum of martingale and then some kind of increasing process, which is predictable. Is it not? That is, we have seen it for the discrete case, but same kind of analysis can be done it for the continuous setup. So if I just take the differences, means B square T minus T, okay, this is a martingale. It's a martingale. Okay, one can do it directly, the proof, but what I'm saying is that is the consequence of, you can think of that why you can expect that B square, and then if I subtract something that gives you the martingale. So basically this T actually you will see that it is the quadratic variations of your Brownian motion to the interval 0 to small t, that is T. Okay, I'm not going into that, but this is a martingale. This is a martingale also. Okay. And we're also considering so-called the exponential martingale. So who has done the course, I think MTL 733, that stochastic of finance course. So you have seen there the application of exponential martingale. Okay, so what it says that if you define mt, which is exponential of say a bt minus a square by 2t. Okay, so this one is a martingale. Not only that, expectation of m0 or expectation of mt, which is actually equal to 1. This has a many applications. This exponential martingale has a many applications, in particular in finance. Okay, it has many applications. So maybe since you have done some major theory course and so on, you know so-called the Radon-Nikodym derivative, okay, Radon-Nikodym theorem and so on. So using these things, actually one can find out the probability measures and all these things. Okay, but what I try to say that the exponential martingale has a many applications. So here we have seen that if I define mt in this form where a is any real number and bt is a one-dimensional Brownian motion, then mt is a martingale, that is called the exponential martingale. Okay. So now we will discuss some applications of martingale inequality for Brownian motion. Okay, so what I try to say is the following. Now suppose, maybe I can think of as a theorem. Suppose Bt, this is my Brownian motion, one-dimensional Brownian motion. Okay, or the standard Brownian motion. Now for every t, I am saying that probability of supremum over S is less than equal to T of B of S, which is greater than or equal to some alpha. Okay, so for alpha is positive and every t greater or equal to 0, these things is less than or equal to e to the power minus alpha square by 2t. Okay, this is first one. And second one is that probability of supreme over S is less equal to T. What can you say about that mode of Bs is greater or equal to alpha? This is less than equal to, we can expect maybe 2 times e to the power minus alpha square by 2t. Okay. So using the martingale inequality. So what is the martingale inequality? What we have seen that if you have a say semi-martingale, and then what you can know that probability of supreme over say S less equal to T, some MT, say greater than or equal to alpha, this is less than or equal to 1 by alpha, expectation of M of T, the highest point. Okay. So this part you have, for that case I need the positivity, otherwise I need to put that M plus of T. Is it not? So we try to use these things to prove this inequality. How to prove it? Let's see. So idea is actually, see, I have these exponentials and so on. So that means I need to put it in a exponential form. In particular, what I know that if a is greater or equal to b, then exponential function is increasing. So I can write down that a to the power a greater or equal to a to the power b. Is it not? So if I define the exponential martingale, so for a is positive, you consider the exponential martingale. mt, which is I'm considering exponential of abt minus a square by 2 times t. Okay, so now my claim is that probability of supreme over s is less equal to t, b of s is greater than or equal to alpha. This thing is same as probability of supreme over s is less equal to t, ms. This is greater than or equal to e to the power a alpha minus a square by 2 times t. Okay, this is the tricks. This is because of the monotonicity property of your exponential functions. So means if the omega lies between this event, that is subset of my this event, and hence the probability which is less than equal to that part. This is the IC only. Okay. So now what I know that ms, this is a martingale, it is exponential martingale, and then I can use, and also it is a non-negative, is it not? It is also non-negative. So I can use my martingale inequality. Okay. So what it says that this should be less than or equal to 1 by this thing. So which I can write down there, this is e to the power minus a alpha plus a square by 2 times t, and then exponential of m of the highest point, which is t, m of t. And as I told you that MT is a martingale, and for the martingale, what is the property? We know that expectation of MT is equal to expectation of MS for all T and S, and hence expectation of MT is constant, which is same as expectation of M0. Now M of 0 is nothing but actually 1. Is it not? M of 0 is nothing but 1. So expectation of M0 is equal to 1, and hence I have this is same as e to the power minus a alpha plus a square by 2 times t. Okay, so now this holds for any a positive, is it no? So this holds for any a positive. So that means what I can write down, this implies since this holds for any a positive, I can take the minimum over a is positive, so that I can also have that upper bound. So probability of supreme over s is less than or equal to t, bs greater or equal to alpha. This is less than or equal to minimum over a is positive, e to the power minus a alpha plus a square by 2 times t. Okay, now you calculate, you know how to find out this minimum and so on. So you think of the derivative with respect to a and then you put a prime is equal to 0, and from there you find out what it will be. So you'll see that whenever a is equal to alpha by t, then the minimum happen, and that is given by e to the power minus alpha square by 2t. Okay, you check it this part. So at the end, what I have, probability of supreme over s less than equal to b of s greater equal to alpha. This is less than equal to e to the power minus alpha square by 2t. Okay. So this is applications of martingale inequality. Since I want to show this part, the idea is to somehow use the exponential martingale, and I can do it because exponential functions is basically increasing. No, it has a nice property. It is a monotonicity property because of that. Okay. So for the second part, this is same. Only thing is that you need to know that if say x is a Brownian motion, then minus of x is also a Brownian motion. Okay, satisfy the same property. X and minus x, it is a Brownian motion. If x is a Brownian motion, then minus x is a Brownian motion. I think I have given you at some point the remark that if xt is a Brownian motion, then minus of xt will be again a Brownian motion because it satisfies all the conditions of the definitions to be a Brownian motion. Okay. So we try to use that part. Let's see what I have to use. I have to use probability of, because this part I know. So I try to write down in this form. So probability of supreme over s is less equal to t mod of b of s greater equal to alpha. This part actually I can write down in a two terms, which is less than equal to probability of supreme over s is less than equal to t b of s greater equal to alpha. This set plus probability of this should be the infimum because it is a minus things I have. S is less equal to t. Now b of s, this should be minus alpha. Okay. So now this part actually I can write down. I can put as it is. This is probability of supreme over s is less equal to t. B of s is greater equal to alpha. And then plus probability of, so these things. So now what I know that supreme over minus things, that should be the infimum. This is I can put supreme over s is less equal to t minus of minus b of s. This is less greater equal to, okay, because minus actually we are putting minus alpha. This is less than, so I have to put, okay, all are less than or equal to. So if we put that minus things, then should be then supreme over that part. So this is greater or equal to these things. Is it not? Because if omega is in here, then actually omega should be actually here. Is it not? In this set, and then I have this part. So now bs and minus bs, they have the minus b is again a Brownian motion because b is a Brownian motion, so minus b is again a Brownian motion. So minus b dot is also a Brownian motion, and hence by 1 actually I can write down. So this is same as my 2 times probability of supreme over s is less equal to t, b of s is equal to alpha, and this is less than equal to 2 times e to the power minus alpha square by 2. Okay, so the striking property here is that if x is a xt, which is a stochastic process, if it is a Brownian motion, then minus of xt is a Brownian motion. Not only that, we have, I told you that, okay, if you start with capital T, then b of t plus capital T minus b of t. So if you define as my xt, this is again a Brownian motion. And not only that, if I consider this capital T is a stopping time, still it will be a Brownian motion, and that is also independent of all small bt, where t is less than equal to that capital T. So that is called the strong Markov property. We are not going into that, but it satisfies. Okay, that is called the strong Markov property of the Brownian motion. Okay, but this one actually you can check it using the property what you know for the Brownian component. Then you can see that xt is again a one-dimensional Brownian motion. Okay. Okay. This is the translation invariant. No? Oh, sorry, this should be capital T. Otherwise, then actually at t is equal to 0, it should be 0. No, it should be capital T. This is the translation invariant in this sense. Okay. So that's all for the martingale part. And I'll start with the next chapter. Okay, so I think I have given some 2-3 assignment problem for this continuous martingale. So as I told you that if you know the discrete martingale, all the results can be extended to a continuous martingale. Already you have seen the proof, no? Basically, you are discretizing in some sense, and then you are using the path property of your given stochastic process, which is in general we are considering that the right continuous with left limit exists, and then you try to use as each discrete level. So if you discretize things, or you consider the sequence of the time. So at discretized time, it is a discrete time martingale, and then you use the theorem, whatever you know for the discrete time martingale, okay, and then you try to use the continuity property, path continuity property, to have the results for continuous time. Okay, that is the general result. Okay, so for the Brownian motions, there are many properties and so on. I am not going into that here. Actually, I just try to say that okay, Brownian motions is again a martingale and so on. It has a nice property, in particular the exponential martingales and so on. And using your Brownian component and also the property of a martingale or the martingale inequality, I can find out this estimate actually, whatever I did today. Okay, so now I will move to so-called the Markov chain. So basically what it remains that I will talk about the Markov chain and then continuous time Markov chain. So Markov chain means basically it is discrete, it is like a sequence. Okay, and later on I will talk about the continuous time Markov chain, and then I will talk about some application. In particular, in the continuous time Markov chain, there is a particular process called birth and the death process. I will discuss about that, and then applications in queuing theory. Okay. So if you see that one example, one exercise I have given from in your minor exam, that is also one can think of as a applications in queuing theory, because you are waiting to enter to the booth and so on. So we'll see more on that, but again you don't need to apply this queuing theory and so on concept, but there actually you will see the renewal as a renewal things and so on, actually you can think. So that is why actually I have given there. Okay. So Markov chain means basically what it says that, so we know that the Markov property, is it not? We know that the Markov property. So Markov chain means basically a stochastic process which satisfied the Markov property. Okay, but in this case, the state space, they are finite or countable. Okay, they are finite or countable. That is the main issues. So it's kind of the integer value I can think of is the state space. Otherwise, it satisfies your Markov property. That is called the Markov chain. And in a continuous time setup, actually, whatever you have, again the state space or in the target, the where it takes values, that is basically integer value. So as a definitions, I can say, so if you remember, whenever I'm saying that the Markov property and so on, so basically what it says that if you know the present state, then the knowledge of this past history, it has no influence to the probability structure for the future state. That means it is independent of the past. Is it not? That is the Markovian property. Okay, so in particular, what I try to say is the following. So I say that a sequence of random variables xn, okay, with discrete state space. That is important. So now state space is the discrete. So if you remember the classifications for stochastic process, no, we consider that discrete time, discrete space, and so on. So it is basically that things: discrete time, discrete space for the Markov chain, and it satisfies certain special properties. So Xn with discrete state space. So this discrete state space, it may be countable or it may be finite. Okay, so both we will consider it, and then we will give more emphasis on finiteness, because that is in the real life problem is more important. So it may be countable or finite. It cannot be uncountable. It's called a discrete time Markov chain. In short, I put DTMC. Okay, so whenever I consider the continuous time Markov chain, I will write down CTMC. So this is in short DTMC if the following conditions hold. So what it says that probability of x of n plus 1, this is actually j, because this is in a discrete setup. Okay, j is in your discrete state given all the past informations. That means x of n is equal to say in, x of n minus 1 is equal to I of n minus 1, and say x0 is equal to I0. If you consider what is the probability that x of n plus 1 is equal to j, I know all the informations that x of n is equal to in, x of n plus 1 is equal to in, and also on. This is same as that probability of x of n plus 1 is equal to j given x of n is equal to in. Okay, so that means what it says that, and this should hold for all n. This should hold for all n, and for all these states, say I1, I2, in, j, all in your state space. So now to define these things, what I need to know? I need to know that the probability of this thing should be positive. So provided, because this is a conditional probability, no? This is a conditional probability. We know that, okay, A given B is that probability of B should be positive. Then I can think about what is the probability that the event A occurs. You know that B already occurred. So this is the things provided probability of xn is equal to in, xn minus 1 is equal to in minus 1, x of 0 is equal to I0. This is strictly positive. So that's what I'm saying. This is just definitions of Markov chain. What it says that if you want to predict or what is the probability of the future given all the information, you don't need all the past information, only you need the present information. This is same as the probability of xn plus 1 is equal to j given x of n is equal to I of n. So if you remember, whenever I defined this Markov property there, no, I exactly wrote down in that form, but with respect to some Borel measurable functions I wrote down. Is it not? But that is says means one can use that all these definitions, which they are basically equivalent. Okay. So what it says that if you know the present state, say xn is equal to y, the knowledge of the past history. This is the past history. Xn minus 1 up to x0, it has no influence on the probability structure of the future state xn plus 1. Okay. So if the sequence xn is a Markov, something like that, suppose this is your state space and so on, all these things. So this is your, you start with x0 from here, then x1, x2 and all these things. So you want to know now I am, this is in state, n state, I am here. So I am, what I'm saying that I am here. So what is the problem that I will go to there? You don't need to know all these past things. If it is a Markov, you only need that from where means you need to know only the present state. Okay, so let us consider one example. So in one word, basically it is independent of the past. Is it not? It is independent of the past because there is no influence, means it is independent of the past. So suppose you toss a coin, okay? So coin toss. You toss a coin repeatedly and you consider xn, which is the sequence, which is the number of heads. I denote this is the number of heads in the first n toss. Okay, so now we see that the values of xn actually takes the discrete 0, 1, 2, 3, 4, and so on. Is it not? So I'm saying this xn is a Markov chain. Why this is so? Because the number of heads obtained in the first n plus 1 toss, it's only depend on the knowledge of the number of heads obtained in the first n toss. Is it not? So in first toss, second toss, third toss, and so on. So you are getting head, tail, and so on. It does not matter. Only you need that, okay, x of n is equal to say 1. And then x of n plus 1, it will be 2. Or again, it will be 1. It depends on your, no, the present toss in n toss, whether you have head or not. Then it will increase by 1 and or it will remain same. So this is the number of heads in the first n toss. So it is independent of the future. Sorry, it is independent of the past. So it only depends on the knowledge of the number of heads which obtains in the first n tosses. So you can see that it is a example of a Markov chain. Okay. Another example I try to give you, that is called a simple queuing model. Means there are many things and so on, actually one can triangle. So now suppose at time 0, 1, 2, these are the times at which an elevator it starts. Okay. So now what we assume that only one person can be transported by the elevator at a time. Okay. So elevator is started and then people are coming and then waiting. So only one people can go to the lift. Okay. And then maybe go up and down. So between the times n and n plus 1. So between the time n and n plus 1, what actually yn denotes the number of people who wants to get into the elevator ride. Okay, so that means, see, people are coming and then you need to wait, and the elevator is coming at time set t is equal to 0, t1, t2, and t3, and then only one people can enter to the elevator. So this yn, which is basically the number of people in between time n to n plus 1, because see at time n, suppose elevator go up, and then at and again n plus 1 it will go up. So in this between 2 times n and n plus 1, what I denote that yn, which is kind of the number of people who wants to get into the elevator. So now suppose this yn, they are independent. Then what will be the queue length? If I denote my xn, which is the queue length, that should be maximum over 0 x of n minus 1 minus 1 and then plus y of n minus 1 for n greater equal to 1. Okay. And okay, now you suppose x of 0 is equal to 0. So xn is basically the number of or the queue length of the queue xn before the start of the elevator at time n. This is my xn. So now my claim is this xn. So claim that xn, it's a Markov chain or DTMC. How to prove it? Okay. So x of I, if I is less equal to n, this can be expressed as in terms of y1, y2 up to y of n minus 1. And that means yn is independent of x0, x1 up to x of n. This part I have. Okay, so we start with say x0 is equal to 0, that is okay. Because each xi where I is less than equal to n, this I can express in terms of y1, y2 up to y of n minus 1. And each yi's are independent, hence I can think of that yn, this is the independent of this vector x0, x1 up to x of n. Okay, so if I of n is greater equal to 1, this is my case 1 maybe, then what I have, that probability of xn plus 1 is equal to I of n plus 1 given xn is equal to in, x of n minus 1 is equal to in minus 1 and so on, x0 is equal to I0. This what I can write down, this is same as probability of xn plus 1 is equal to I of n plus 1. This is the property of conditional probability. And then I have xn is equal to in, xn minus 1 is equal to I of n minus 1, so on, x of 0 is equal to I0 divided by probability of xn is equal to in, x of n minus 1 is equal to I of n minus 1 and so on, x0 is equal to I0. Is it not? So now what is your xn plus 1 is equal to I of n plus 1? I can think of this is, I can write down in terms of my y of n. Okay, xn plus 1 is equal to I of n plus 1. So from there, because I put it xn is equal to I of n, which is greater equal to 1. Now if you look at the definitions here, maximum over 0, xn minus 1 minus 1. So if xn, if I put xn plus 1, then the maximum should be this one. So x of n plus 1 is equal to x of n minus 1 plus y of n. So now x of n plus 1 is equal to I of n plus 1. This is same as my probability over y of n, which is equal to I of n plus 1 minus in plus 1. And they are independent because yn is independent of this thing. So I can write down this is probability of xn is equal to in, x of n minus 1 is equal to I of n minus 1 and x of 0 is equal to I0. And then you have that probability of exactly these things. This is nothing but my probability of yn, which is equal to I of n plus 1 minus in plus 1. And this again I can write down in the same way. This is probability of xn plus 1 is equal to in plus 1 given xn is equal to I of n. Okay. So that means what it says that if xn is equal to in, where in is greater or equal to 1, in that case it is a Markov chain. So I have to check that in should be also 0. In that case also you can conclude the same thing else. So if your I of n is equal to 0, then I of n is equal to 0. What is I of n? I of n is x of n is equal to I of n. So now you look at the maximum should be 0, and hence x of n plus 1 is equal to y of n. So x of n plus 1 is equal to y of n. Okay, so in this case, what I have, probability of xn plus 1 is equal to I of n plus 1 given xn is equal to I of n, x of n minus 1 is equal to I of n minus 1, x of 0 is equal to I0. This is same as probability of xn is equal to, which is basically yn, I of n plus 1, xn is equal to I of n, x of 0 is equal to I0. Okay, this part, and then probability over x of n is equal to in, x of n minus 1 is equal to I of n minus 1, and x of 0 is equal to I of 0. Now again this yn and these are the independent, so I can take probability that this is same as my means probability of AB is equal to probability of A, this is probability of B. So from there what I have, this is probability of yn is equal to I of n plus 1. Now this is same as I can think of, this is probability of x of n plus 1 is equal to I of n plus 1 given xn is equal to I0, which is my 0 now. Okay, this is exactly same because in is equal to 0. So this implies for in any cases what I have, that xn is a Markov chain. Okay, xn is a Markov chain. So in my previous example, it was easier because we know that the at that n plus 1 level, whether head is coming or not, it depends on knowledge of the head coming in the n toss or not, first n toss or not, is it not? So it is independent of the past. That is why actually it was easier, nothing to prove. But in this case, it is exactly not the case. So you have to prove it using the definitions. Okay, this is called, this xn is called a simple wing model. Okay, so now we try to look at various properties. In particular, suppose my xn, which is a Markov chain, then what can you say about the product things? Product things means basically what is the probability of xn is equal to I of n, xn minus 1 is equal to I of n minus 1, so on, and all these things. Okay, so what I try to say is the following. If xn, okay, this is the notation I generally use, x of n such that n greater equal to 0 is a Markov chain, then if I choose I0, I1 up to I of n is my state space S, we have, so for all these things, probability of xn is equal to I of n, x of n minus 1 is equal to I of n minus 1, x of 0 is equal to I0. These things I can write down, that probability of x0 is equal to I0, product of k is equal to 1 to n, probability of xk is equal to ik given x of k minus 1 is equal to I of k minus 1. Okay, if you know the individual conditional things, then you consider the product of that, then you will get the probability of this event xn is equal to in, x minus 1 is equal to I of n minus 1, x0 is equal to I of 0. Okay, let's do the proof. Because at some point actually you may know these things, no, probability of xk is equal to ik given xk minus 1 is equal to ik, individually we know. Okay, then we want to know what will be the probability of xn is equal to I of n, xn minus 1 equal to I1 minus 1, and so on, x0 is equal to I of 0. Only thing is that it is given to you that xn is a Markov chain. Okay, it's a Markov chain. So how to prove it? So if you look at from the right hand side, probability over x0 is equal to I0, product of k is equal to 1 to n, probability over xk is equal to ik, given x of k minus 1 is equal to I over k minus 1. These things I have. So now this is actually I can write down. This is actually equal to probability of x of 0 is equal to I0. Then product of k is equal to 1 to n. What I can write down? This is probability over xk equal to ik. Say probability of xk is equal to ik given xk minus 1 equal to ik minus 1. This is my same as what I can write down is the following. That probability of xk is equal to ik, xk minus 1 is equal to ik minus 1, x of 0 is equal to I0 divided by probability over xk minus 1 is equal to ik minus 1, x of 0 is equal to I0. Is it not? Because it satisfies your Markov property. It satisfies your Markov property. So probability of xn plus 1 given in, and then conditional on these things, you have this part. So now if you try to write down probability of xk is equal to ik given xk minus 1 is equal to ik minus 1, this is same as probability of xk is equal to ik given x of k minus 1 equal to ik minus 1, x of k minus 2 is equal to ik minus 2, and so on, x of 0 is equal to I of 0. That is using the property of your Markov chain, and that is actually I try to write down in terms of the probability. So I have these things. So now you see it is the product, so all these got cancelled out. Only thing is that you are remaining this part. So this is same as my probability of x of n is equal to I of n, x of n minus 1 is equal to I of n minus 1, so on, x of 0 is equal to I0. This is nothing else, just using the properties of Markov chain. Here actually I am using this part, that probability over xk is equal to ik given xk minus 1 is equal to I of k minus 1. This is same as probability of xk is equal to ik given xk minus 1 is equal to ik minus 1, xk minus 2 is equal to ik minus 2, and x of 0 is equal to I of 0. Is it not? This is the Markov property. And now this one actually you can write down exactly this one, probability of xk, this is on the intersections and divided by this part, exactly this part. Now you have a product, so basically it got cancelled out, only that whenever k is equal to n, this part is remaining, so that is actually I wrote down here. Okay. So this is the, it says that if xn, it is a Markov chain, then if you consider the any state, say I0, I1 up to I of n, which is in state, then probability of xn is equal to in, x of n minus is equal to I of n minus 1, and so on, x0 is equal to I0. This is same as probability of x0 is equal to I0. And then product of k is equal to 1 to n, probability of xk is equal to ik given xk minus 1 is equal to I of k minus 1. Okay, let us make some definitions and then we will talk about more on that. So now suppose xn, this is a Markov chain, it is given to you. Okay, so what is the probability mass functions of xn? That is nothing but basically pj of n, which is probability over xn is equal to j. That is the notation I wrote down. Pj of n. So probability of xn is equal to, that is the probability mass function, no? Because xn taking the values only discrete. So j is equal to 0, 1, 2, so on, or something like that, whatever it is there. Okay, so now I'm defining that pjk, say mn, which is by definition, what is the probability that xm is state k given, means xn will be state k given xm is equal to j. What is the probability that we start with at time m with state j? Okay, what is the probability that it will be state k in n step? That means xn is equal to k, where 0 less than equal to m is less equal to n, and jk is in my s. This is pjk m of n. Okay, so we say that it is a homogeneous Markov chain. Okay, so x of n is called homogeneous Markov chain if it depends only the difference m minus n. Okay, that means pjk mn only depends on the difference n minus m. So throughout our study, we will talk about basically the homogeneous Markov chain, mainly homogeneous Markov chain. So it's called the homogeneous Markov chain if pjk depends only the difference m minus or n minus m, because I put n is bigger, so n minus m. That means basically it does not matter from where you start it. Is it not? In which step you start with? Is it m or n or something like that? It does not matter. If I start with say 0 and it is my n, then it is fine, because the difference is basically n. Okay, so this is n minus m. So if we start with 0 and then this is n minus m, that is also fine. Because if it is a homogeneous, it depends only on the differences. And we are mainly interested with this homogeneous Markov chain. Okay, so for the homogeneous Markov chain, we define the m-step transition probability. For homogeneous Markov chain, we define the m-step transition probability. Denoted by pjkm, which is given by, so pjk of m, this is actually probability of x of n plus m is equal to k given x of n is equal to j. So we start with n, time level n at state space j. Now we are going to n plus m. Now the difference is m. That means in m step I am reaching k. What is the probability of that? That is I denoting the pjk of m. That means the m step transition probability. Okay. So now I can think of, no, I can put n is equal to 0. This is x of m, that is m. I can, because it does not depend on the m of n, it is only depends on the differences. Okay, so the n step probability I can use exactly in this way. So exactly these things actually I can think of. So what will be that p j k of 0? This is by definition. This is I define. Okay, everything we also define here. So because this is we say that at m step, is it not? So then what is p j k of 0? This is basically that means probability of xn is equal to k given x of n is equal to j. Means you start with state j and then we want to know what is the probability that x of n is equal to k. Okay, so that's is basically the direct delta, means 1 if j is equal to k, and for j is not equal to k, that is actually 0. That is the by definitions. This is trivially actually. So probability of jk of 0, which is the delta jk. Okay, the direct delta of jk. So now I have defined the m step transition probability p jk of m. So now all these things are less equal to 1. I am defining the transition matrix, m step transition matrix, that I denote by p of m. So the p of m has the element nothing but my p ij of m, where I j in my state space. So it may be of infinite row and column, it may be infinite depending on whether that state space S is finite or countable and so on. Okay, so now the probabilities, this is called the one step probability. I denote as Pij. This is by definition that is called the one step probability. So that means you start with xn as state I, then we want to know what is the probability that x of n plus 1 is state j. Okay, so Pij, so first I means it start with this state and then it will go to state j in one step. That is a one step probability. So generally we try to put also 1 or without 1, that is in n plus 1. Okay. And the probability distributions pi, I written as a pi I, which is I is in my S. What is my pi I? Pi I is equal to probability of x of 0 is equal to y. That is called the initial distribution. Okay, this is called the initial distribution because you have the sequence, x0, x1, x2, and so on. And x0 also it will take maybe 0, 1, 2, 3, and so on in the state space. Then we want to know what is the probability of x0 is equal to y. That I denote as a pi I. That is called the initial distribution. How the initial is distributed. Okay, the initial distributed. And the transition matrix P, I define P of M in this way, that is the M step transition matrix. So now P, which is again Pij, this is one step transition matrix. Ij is in my S, it is called the transition matrix, sometimes one step transition matrix, or in general, we call it as a transition matrix. Okay, we are not putting as a one. So this is the transition matrix, or sometimes called the stochastic matrix. So the stochastic matrix means basically we know, maybe you know the definition. So that if all the elements is not negative, means greater equal to 0, and summation over j over, so Pij is greater equal to 0, summation over j, Pij, j is in over s, this is actually equal to 1. This holds for all I in my state S. That is why it is called the stochastic matrix. Okay. So Pij, that is actually 1, is a stochastic matrix. Okay. So we have seen this queuing model, no, simple queuing model, and then try to find out the transition probability matrix P. So what is your Pij? Pij, this is nothing but, so okay, example. For simple queuing model. Already we have wrote down that part. So now Pij, what is that? That means this is a one-step transition matrix. So it state with xn is equal to I. We want to know in n plus one step, it should be j. Is it not? So now if I is greater than 0, so if I is greater than 0, xn is equal to I, and then what is this? This is nothing but your probability over yn is equal to j minus I plus 1. Is it not? That is why you wrote down, no, that x of n, which is maximum of 0, x of n minus 1 plus y of n minus 1 for n greater equal to 1. So now that is why I put that if my x of n is equal to I, which is positive, then the maximum thing should be x of n minus 1. Okay, and x of n is equal to I. So y of n is equal to minus j plus 1, all these things. And if your I is equal to 0, this is nothing but in that case x of n plus 1 is equal to your y of n, and hence it is same as your probability of y1 is equal to j. So now if you consider the probability mass functions of yn, if I denote that pj, which is that probability of yn is equal to j, okay, because they are independent, hence basically that p1, p2, p3, pn all are same. That is why I put it pj is equal to probability of y is equal to j. So then the what will be the transition matrix? Then the transition matrix P, okay, of the Markov chain, what is given by P should be what? So this should be P0, P1, P2, P3 and so on. P0, P1, P2, P3, so on. Now P0, P1, P2, P0, P1, P2 and so on. Okay, this is the case. Okay. So next I'll talk about something and then I will stop. So what I'm saying that if you know the transition matrix along with the initial distributions, then you can completely specify the Markov chain Xn. So suppose I have given you some arbitrary Markov chain Xn, okay, but I am giving you the transition probability matrix, that P matrix P, and the initial distributions. So then my claim is I can find out whatever I want, means I can specify the Markov chain, means any kind of thing I want, say probability of say xn is equal to 1 given x0 is equal to something, or whatever the all kind of combinations, whatever kind of combinations you want, I can always find out. What I need only, I need that the transition matrix and the initial distribution. Let us see checking on calculations. Okay. So for that you will see that the previous lemma we are using. So example may be, what I'm saying that suppose I have a Markov chain xn. This is a Markov chain with state space S. I'm considering just finite thing, say 0, 1, and 2. So the value of xn, it takes 0 or 1 or 2. Okay, and I have given you the transition matrix P, which is 3 by 4, 1 by 4, 0. Okay, 1 by 4, 1 by 2, 1 by 4, 0, 3 by 4, 1 by 4. So you see that if you add in this way, actually it gives you 1, but not in this way. Okay. Okay. I need initial condition, initial distribution. So I'm giving the initial distributions is uniform in the sense that probability of x of 0 is equal to I, which is 1/3. I'm giving you for I is equal to 0, 1, and 2. Okay, it is given to you. So then I can find out whatever I want. In particular, if I try to find out say probability of x1 is equal to 1 given x0 is equal to 2. What is this? X0 is equal to 2 in one step. Okay, so that means this is nothing but the P21. Is it done? So now the P21 actually I am coming from here. This is, you can think of 0, 1, 2, 0, 1, 2. So P21, 2, 1 you have. Is it? Oh, sorry. 0, 1, 2, 0, 1, 2. Yeah. 2 P21 actually you have. So this is nothing but the 3 by 4. No? P21, this one 3 by 4. And if I just want to know say probability of x2 is equal to 2 given x1 is equal to 1, this is nothing but see x1 and then you see that again 2. So this is P12. What is your P12? 1, 2. This is 1 by 4. You have 1 by 4. P12, this one. Okay. So now I want to give you a little more. So I want to give you, say, try to find a probability of x2 is equal to 2, x1 is equal to 1, given x0 is equal to 2. I want to find out this one, whether it is possible or not. Yes, this is possible. So these things actually I can write down. This is same as my probability over what I can put it. This one, see x2 is equal to 2, x1 is equal to 1, x0 is equal to 2 divided by probability of x0 is equal to 2. I can find out. Okay, and then I can use my previous one. So this is probability of x2 is equal to 2, x1 is equal to 1, probability of x0 is equal to 2, and so probability of x0 is equal to 2 you are having. So then you have probability of x2 is equal to 2 given x1 is equal to 1. Then probability over x1 is equal to 1 given x of 0 is equal to 2. Is it not? Because this one what I can write down. This is nothing but probability of x2 is equal to 2, x1 is equal to 1, x0 is equal to 2 divided by probability of x0 is equal to 2. Is it not? So now this one what I know that if you just remember here this lemma that the product things, no, probability xn is equal to in and all these things, it is a given that it is a Markov chain, I can write down this product form. So now you see that this initial I got cancelled out. So from here actually I have x2 is equal to t given x1 is equal to 1. I wrote down probability of x1 is equal to 1 given x is equal to 2. That is I wrote down. Okay. So now this one is nothing but what I have. This is what? It is this one, and x1 is equal to 2 is basically this one. This is 1 by 4 times 3 by 4. is equal to 3 by 16 and so on. So I've given you just the 2-3 things, but you can find out whatever you want. That is I'm saying. Means you can completely determine the Markov chain. You can completely determine the Markov chain. If you know the probability transition function, the matrix, probability transition matrix, and the initial distributions. X0 is equal to 2. Okay. Here it got considered, but maybe at some point we need to have these things and so on. Okay. Okay. I stop now. So I'll talk about more on Markov chains and so on, all these things. So as I told you, most of the time actually we'll try to find out whenever my state space S is finite, because it is discrete, that is fine, but mostly in applications, okay, there are both, which is countable as well as the finite, but most of the cases we try to look at the finite case, and for the finite case you have some special treatment, maybe something will be available there. Okay, so I'll stop now. Is there any question?